So we have a very interesting session for you on soul spectroscopy. It's a workshop, so it's not just a lecture. It's going to take about 1 hour. It's really hands-on. I'll open the data and I'll be fitting some models, and maybe things not going to work. I did it on my workstation yesterday, but my laptop can run out of RAM or something. But I can show you all the results. And yeah, I'm Tom Hengl. I'm a director at OpenGeoHub, and I work on this project called Open Source Spectral Library for almost 3 years. And so I'm going to talk a bit about that project, OSSL, and I'll show you how to access data. I'm very proud of that project. It was with a very noble goal to make soul spectroscopy data way more accessible, open, and to establish a development community. And I'm very happy with this project because it did happen. There is a community, and people are extending, and they're building their own software, and they're publishing, and it's really taking off. But I will show you how to access this data and how you can use it. Then I will take one data set, which is from the OSSL. It's a one smaller data set, so I can run it, play with it on my laptop. And it's produced using NeoSpectra scanner, the handheld scanner. And I will show you how this could be used potentially for near real-time soul observation measurements. It is mainly USA. There is some data from Africa and from Europe, but it is a US data set. For simplicity, I use a data set that you can download and reproduce. But my colleague Kostas here, he's going to talk about the data from the Air for Soul Health project. After I finish with the demo, then I will pass it on to Kostas, and he will show you this data also we created in Air for Soul Health. Although this data is still in processing, so it's under hub still. While this data, I'm going to use this NeoSpectra Soul Spectral Library on OSSL. This data, it's really published, and you can use it, you can download it, you can test it. And I was very interested in this data set because it is a bit less expensive instrument, less spectral bands, bit narrow part of spectra, only up to 2,500 nanometers. And so we are trying to improve the accuracy. And one of the ways to improve accuracy is to do this, what we call a data fusion approach. And that means you have the spectral scans, but you can also, for example, I will plug in a Landsat information. So I will put in spectral reflectances from Landsat. So at that point, I know the spectral signatures, but I also have the Landsat spectra. So I do kind of a data fusion. So it's a spectra from the space and spectra from the ground. And we want to see whether it helps. I tested it yesterday, it doesn't help. to break the story, but there's something. I see something, but it's less than what I expected. So, but you know, I'm a scientist. I'm not a businessman. I don't need to cheat. I tell you honestly, I tested it. It's limited. I am enthusiastic about it. I would like to test it more and see maybe for some other data and also bigger data. So that's about the OSSL. So OSSL, we imagine, in very simple terms, we imagine to make OSSL to be like what is GDAL for GIS people. You know, open source driver that everybody can use, something like an Android for phone, something like, you know, Wikipedia for encyclopedia information. We wanted to make it really widely used, open data, open infrastructure, and then we call people to contribute. And there are many people that send us data now. And my colleague Jose Safanelli, he usually gets this data. He now maintains it. He maintains the data and everything. And we have a publication in PLOS ONE about OSSL. It really explains everything. so I don't have to maybe talk too much about it, but you can read in +1 about OSSL. It is also a GitHub project, so all the software we make, also manuals, tutorials, models, and workshops we do, it's all on GitHub, usually MIT license or CC BY license. So it's also, if you're a business, you can also use it, and you can use it for commercial purposes. You don't have to contact us. You only have to mention that it's a OSSL library. This is a general framework. So we started first, there were quite some bigger data sets. The biggest data sets at that time, it was a European Lucas that they scanned in a NRI part of spectra. And then our American colleagues at Lincoln, they spent 15, 20 years actually scanning, and they produced this library called SSL, Kellogg's Lab Source Spectra Library. Then we got AFSIS data, then we got some Central African data, and then there was a little data set that we added slowly, and we always reference them. And eventually we got quite some data integrated. It is available in this, if I go to Explorer, so you can see it in the source spectroscopy.org, which is the homepage of the project. Now you can see all the data sets. So if I zoom in, you can see somewhere in Africa, I don't know. I can see there's, for example, more data here. So I just keep on zooming in. Sometimes the data are clustered. Let's say this one is here. So there's 2 data sets. And for this one, I think you can even see the spectra. This is, by the way, this is our Shiny app. Imagine you can build our Shiny app that looks like an app. It's a WebGIS. And it integrates with the Plotly, also Plotly open source. So you have an interactive view on the spectra of the all the scans that we have in OSSL. And so you can access all these things, and you can also access a part of the OSS, the original training data, which is of course very important. Then the second part is the models we fitted. So we feed these models. The models also put there on the Google Cloud, I think. And so the models also available. So you don't have to feed the model. You can just use the model to predict. So that's also available. Then we also made the documentation. And this is available on the, let me see, that's on the docs. So spectroscopy.org. So you have this documentation, technical documentation that explains how was the data created, how to access it, how to easily access. So usually from Google Cloud Storage, and how were the models fitted. So you can see the models, how they were fitted. So if you think you can improve the models, you can go ahead and prove it, and you show us, I have a better model. And we are very happy to use your model as long as it's based in open source, and we can rerun everything and update. So that's a OSSL in a nutshell. Let me see. This is just to show you basically the spectra today. We have 2 big clusters for spectral scans. One is the MIR. MIR is this big Bruckner instruments. There's this couple of producers. These instruments usually cost about $80,000 to $100,000. So they're very heavy, like 80 kilos, but they can scan more samples, and they have a wider spectra, up to I think 3,500 nanometer or more. So they really cover not only near infrared but shorter and mid infrared, and so they're a bit more expensive. So that's the MIR. It's this one here. This is the MIR, and this one is the NIR. you see here, it's Europe has the most of Lucas points well scanned in NIR and made available. And so this is a bit narrower part of spectra, and then special cluster is the handheld NIR of this NIR, and this is this NeoSpectra spectral scanner. So there's the third cluster. It's not shown here, but we will use it. And you can see here, not all points had a geographical location. Some samples we didn't have a geographical location. They just had some location of the county or the town, you know. So we tried to geocode it, but there are 135,000 samples. That's all the information now. There's more, but only about 90,000 they have a geographical location. Then in the OSSL we took about 15 soil properties, about 15, and then we look for the best framework to do calibration, and we did a lot of testing and trial and error, but we finished doing a bit of pre-processing. So we do some pre-processing this step, then we do PCA. This is when we publish paper now. This is also changing to autoencoders and doing a bit more complex compression of the bands. And then we do fitting of the models. And at the moment is the MLR3 machine learning framework in R called MLR3. And then we do 10-fold cross-validation with refitting. And then we produce this accuracy plots. And then in this comparison, you can see that this is the CCC concordance correlation coefficient. It's like how much is it on the one-to-one line. 1 means a perfect model, a 0 failure. Somewhere about 0.7. Jose decided to put like a threshold. So these are relatively poor models. We don't recommend really using this, all these models in this part. And you can see that the V's NIR is always a bit more to the left and lower, so towards this. And MIR is really highest. And for some soil properties, V's NIR, like bulk density, texture fractions, is really on the edge. We don't recommend using it really. That's our results using these models we use. Maybe you could improve, but we don't see that this could work. This also shows you MIR, V's NIR, and NeoSpectra, the handheld scanner. You can see that for organic carbon, actually, for organic carbon MIR, it's really highly accurate. We are getting almost CCC close to 1, so 0.994. So there's no mistake if you have an MIR spectra. If the sample is prepared, it has to be dried and things, then you get a very high accuracy. Then on V's NIR, it's still quite okay, this laboratory V's NIR. But then on the NeoSpectra, it drops to 0.9. So there is a drop. And for pH, it's even higher drop. But you can see that that's the usual difference with the best models. And then some people, as I said, started extending, and somebody just 2 months ago, I think, made a Python package called SoilSpec Data. It is based on the OSSL, and he just sent us a message, hey, I made the library, and so people can now load this in Python. You don't have to look where it is or write. You just code with it, and somebody creates this matplotlib a Python library, and it says this is how you visualize this spectra. And so people now started building upon this and extending. I don't know this person. I mean, I never met him. He just sent us an email, say, hey, I made this library, and we look at it, it's great. And then we usually post about it, and we call that person maybe on some workshops. And I personally had this already 3-4 years ago, I felt like this calibration, because we have the GPS coordinates, we could do this full data fusion. So this is this idea of full data fusion, because you have the spectral signature, that's one part of the data. You can also take all the meteorological data, climatic data, soil moisture, temperature. You have to match the dates, right? You said I was on this day on the field and I took a sample. It was, I don't know, 2nd of September. And I said, what was the soil moisture then? What was the temperature, etc. Then there's some static, because I went somewhere in the field, so I was somewhere in some geomorphic position in the landscape. There's some also long-term climate there. So, you know, there's different climate zones. And then we can take also Earth observation spectral cubes, right? So you have these 4 components, and you put them all together, and you say, now I build a model. And so this is what we call a total data fusion for soil spectral calibration. So NeoSpectra dataset, it's a smaller dataset, and you can download it. It's a public. I will show you also there was a hackathon, and I will now do some modeling for you. Show you that this is this NeoSpectra. It looks like they produce it in Egypt. I think it's made in Egypt. It's about 1.5 kilo in weight. So you can put it in your backpack. You can walk on the field. You can scan also on the field, but John and his team, they usually scan. They bring the samples with them. They dry them. And then they set up a little lab. Very quickly, they will buy 3 of these NeoSpectra, so they can do in parallel. And they will set up a little lab, and then they just scan for like 2 weeks. And then they finish scanning, for example, 1,000 samples. And then they say, here are all the scans. And some samples, they scan multiple times, because you want to scan multiple times, and then you average to smooth out this short-range variability a bit. And that's how they produce it. And then colleagues from Greece, Eleni and Nikolaos, they said, okay, let's do this fusion approach. They read, I was talking about it, I don't know. And then they said, we did it, we think it works. And then they called me, I said, okay, and I joined this publication also. So I looked at it and I said, that's great, that's what I was really dreaming about that, and you did it. And so they published this paper, you can read about it also, how they did it. And this is this data set, right? It's about a bit less than 2,000 samples. I can show you also, I have it now, I just have it in QGIS, and I put also, I put the solar organic carbon percent, solar organic carbon percent. It can be in multiple depths also, they had multiple depths. And I use a log. I convert immediately to log, because everything else is it's a bit skewed, solar organic carbon. So I just convert it to log. So the numbers you see, this is not percentages, this is the log of the solar organic carbon. So if I look different places, so I can see somewhere, so red, darker red means a higher carbon, and the bluish is, so let's zoom in somewhere it's a bit darker. If we see, oh, it falls into some place here. So this seems to be a bit higher carbon in this soil. I don't know why, but it looks like it's an urban place. So that's interesting. So it's somewhere around Detroit. Let me go some other points. So here I can see a bit lower, so much lower carbon. So this is a bit probably some dry areas. Maybe this is here, it's very rocky. I don't know, it looks like very rocky. I know it's a drier part of US. So I can see all these values. So this is the data set. So this is what they did. They compared the different machine learning algorithms. They did, instead of pre-processing using principal components, they use this CNN, convolutional neural networks, to pre-process the original bands, and then they combined this CNN for pre-processing with XGBoost, and that's what gave them the best accuracy, but they added also this environmental covariates. They only had this static and climate. They only used that, they didn't have a Landsat. So they didn't have the data, so I went like, oh, maybe we can extend it with the Landsat. So, and that's what I tried. I got the data on Friday, and on Monday I was over there, let me try. And yesterday I got the final models and I double checked everything, so I know what's happening. It's a similar approach that our colleagues from AgroCares here from Wageningen, they also combine this remote sensing deep learning. But as you know, AgroCare is a commercial business, and even though they have a publication, Geoderma, it's great that they publish and they show, but you wouldn't be able to reproduce this. I think none of the data here is available, and I also actually don't know exactly how they do it. But it's also similar. They do a similar approach. So let's take a look. Let's look at this data now. Just before I look at the data, I want to show you the data is also in this hackathon. We had a hackathon. We gave this data to people to try to predict. And you can see the data is explained in the hackathon. And also the hackathon explains what is the key performance indicators, so RMSE, in the log space. And then people did compete. They did compete, and in Kaggle you get automatically this performance table, and we can see who is the best. So Mikhail Semenov made the best result. So and he tried 6 times. He tried 6 times, and then he came to the first place. But the difference is not huge. This is 224. This is 0.25, right? It's not a huge difference, but eventually it drops. So these people here, they're really off. So they miss something. I don't know. And so you can follow that, and they also provide code. So this is Jose, and he provided code how he will do it. So you can see also how you could do this modeling yourself in a notebook. So here's a computational notebook, and this one is with the MLR3. So you can see how he will do it with MLR3. I don't have time now to go through all that stuff, but you get the idea. Now I will go, I downloaded that data, and from this, I downloaded from the hackathon. So you see there's a train and a test data set. So I downloaded, and I can read it here in R, and I get 1,974 observations of 220 variables. So these are the covariates. These are the static covariates, 220. And one of the covariates is this, for example, Chelsea precipitation of September, the version 2.1 of the Chelsea climate, 1 kilometer resolution global climatic data. And as you see, I get these precipitation values here. And then I can also read, here's the spectra. This is a bit bigger matrix. You see it has 600 columns, and it has the soil carbon. Let's take a look at some of the spectra, how it looks like. So if I look here, so this is some band in the spectra, and I can print up like 20 numbers, I don't know. So I think I have to call this with this name. So I can get the first 10 numbers. So these are the spectral reflectances. It's very abstract, but you have these curves if you plot it. And also very interesting, this data is from KSSL. So data is the samples were taken in different years. So going from 2000 to 2022. So they are taken in different years. And we just created this data set for the world. So we created this data set, which is the Landsat data cube. It's about 160 terabytes. It's quite big. And this is bi-monthly. So bi-monthly, complete, consistent, no clouds, gap filled data cube, spectral data cube for the world. So we created that. There's a publication, you can read about it. And in this data cube, we put it on open land map. So you can also open data, you can use it. It's one image. It's one image of the world. It's 30 meters. So one image is usually about 160 gigabyte. So one image, 160 gigabyte. At 30-meter resolution, one image, it's about 220 billion pixels. Just the land mask, 220 billion. So if you have a 1 year, 6 bi-monthly, so 6 images, it's more than 1 trillion pixels. But these are all cogs, they're all cogs. So you can load them in QGIS and you can put them in QGIS. They're optimized to be used by many people. So do you know about cogs, Cloud Optimized GeoTIFF? It's a data format for big data format that you serve it on S3 or some file service, and it has pyramids and tiles. So when you visualize it like now, you visualize only the things that you look at. It's optimized, it works like a database basically, but it's just a one file. It's very portable, very easy to work with. So we created this data set, and then we want to see whether we can use this data to improve the calibration of the spectra. And this spectra, I'm doing a simple pre-processing. Also, I'm just testing things, I'm not going any fancy things, but I do a very simple pre-processing. I use this Prospect R to normalize the curves. So the curves sometimes can be different. They're like offset, they have an offset. So I want to bring them all kind of on the same line, because I'm only looking for this difference in the curve. I don't look at absolutely where the curves start. So I just bring them on the same line. And then the second thing is I do principal components. That's all very fast. And now I had, I had like 600 bands, and I reduce it to 120 components. I could reduce even to more, like 60, but I use 120 in order not to miss anything, just by chance. But already 60 components is enough, right? So I reduce it, and then, so I have this ready, and now I had to send to my colleagues to do overlay in the space-time cube. I don't do it on the laptop. They can do it on a server, so it's done in like 20 minutes. If I do it on my laptop, it will take 3 hours. Yeah, because I have to look at this big data and, every point in space-time. So I said, can you overlay? Say, yeah, how long does it take? Even less than, I think 7 minutes was done. But so I sent them this, I prepared these points. I sent them the points, and then they did an overlay, and they sent me this GeoParquet PQ they sent me, and then I read it, and now I have also Landsat data. And this Landsat data, it's also abstract. I mean, there's a lot of things, and there's some missing values. And also, let me show you, there's a lot of things. So if I look at the names, because they just really throw it and they say, we overlay it and we derive everything. So you see, I have NDSI, this is the snow index, red band, NDWI water index, thermal band, NDTI tillage index, NDVI vegetation index. So there's a lot of indices. You can derive more indices if you need. There is a library called Awesome Spectral Indices, and you can derive even more. There's a Python library. You can go and say, I want to derive more. And there are specialized indices for soil, for water, for vegetation. So I think there's really hundreds of indices potentially you could derive, right? We don't need them all, so we have to pick up a bit. So we focus more on the soil indices. and we derived some vegetation indices. So here, all these indices, I have them 98. 98 indices, yeah. So I don't have to understand them all, but I have them here in the prepared. And then I have to format this a bit. And then I bind it here. I bind all the data, the line 64. I bind the spectral signatures. I bind the Landsat, and I bind the static covariates. So it's the same as this scheme that we made. So we bind all this data, and then we have finally, we have about 1,000, almost 2,000 by 438. So we have a lot of covariates. It's not a perfect data set. You know, we're fitting a regression model with 2,000 observations of 440 variables. It's not perfect. I mean, I would prefer here to have like 50,000. You know, but this is just for testing. Yeah, I do it also because I need to do it in front of you. And then I can do, for example, let's now test it. Now, if we just do Cubist, which is has a good performance for source spectra for some reason, and this is purely on spectra. So I have the carbon and I have spectra, and I fit a Cubist model. I don't use the MLR3 because it's a bit more complex. I just wanted to show you proof like just so you see. So I use this a bit older Caret package, and you see it's computing now. It's computing on my laptop. It's doing tenfold, I think, tenfold cross-validation, and it will then get, from the comparison, it will show me what is, based on this cross-validation, what is the accuracy of that, just doing the Cubist. I already, while it's computing, so you just get an idea that it takes time, but here's the result. I get R squared for different combination of these neighbors. It goes from 0.70, I think, or 0.74, I think the lowest, and then the highest is 0.79. So from 0.74 to 0.79. So it is good also to optimize that parameter. And then I prepare these other covariates. I prepare the covariates. No, I can stop this now because I think I will be compute. Oh yeah, it finished, great. And then I can see what is the result. So then you get, if I look at this, you get this thing. And then the Caret will select for you what is the best fine-tuned model. And it is a bit of difference. You see, if you don't fine-tune, you can lose on accuracy. And then I can prepare all these covariates. And then I start doing, first I can do fine-tuning. I now test random forest, so I fine-tune random forest. And then I get a random forest model. And then I can do variable selection. This will remove, because I have too many covariates. So I can run a variable selection. And this will take some time, you see. And this picks up from 400 covariates. You ready? From 400, it drops down to 26. It drops down to 26, and R squared 0.71. This is the R squared, not the CCC. But the other one is also R squared. So 0.71. So we can see in the variable importance plot, here's the variable importance plot. We can see that about after 90 trees, kind of stabilizes. This is the accuracy error drop. So it stabilizes, so we can, 100 trees probably enough. And you can see the PC4 is the most important. The PC4 is from the spectra. As expected, you know, if you have the spectral scan, it's the best. And this one band PC4, one component, it's like 90%, 95%. The rest of everything else is very small impact. That's a bit depressing, maybe. And then I visualize this. I can visualize this correlation plots to check what happened. So I can visualize here. This is this PC4, and you can see it's a really very distinct correlation, right? However, some good news is that in these top covariates, we do get NDVI. We get NDSI and NDVI and the green band. They do come up in the variable importance. So there is some hope that it could work. And if I visualize it, this green band, it looks like this. It's a more noisy, but it looks like as it gets darker green, the carbon goes up. So darker green, less greenness. As the greenness goes, the reflectance of greenness goes up, the carbon goes down. And which makes sense, you know, the stronger greenness, it means more vegetation and probably higher soil organic carbon. So there is some correlation, but when I I tried the random forest caret and I tried cubist with these selected covariates, and unfortunately I get about the same accuracy. I get about the same accuracy as if I only use spectra. So because this PC4 is so dominant, it's just a one principal component of spectra. Neospectra helps you determine the carbon really so distinctly. You only just need that one component really, and this helps you so much. So so this Landsat get lost inside. It comes on the variable importance, but it gets lost in the effect on the accuracy. Then I can plot this difference in the accuracy. Oh yeah, then when I do only Landsat, I get R squared going to maximum 0.26. So this is if I only do Landsat, 0.26. And that's also interesting to but it's not something. And then when I plot this shows me we are interested, let's say, in the RMSE, right? So if I do the cubist with spectra and Landsat, I get a bit smaller RMSE than if I use only spectra, but it overlaps. So it is a bit less, but there's an overlap. I don't really drastically improve. Now I just started playing with that. Next thing we will do is we will overlay the whole OSSL. We will overlay it with all of the Landsat we have, and we will clean it up a bit, and I will try one more time to see, and I can try maybe 3 variables to see maybe one variable it helps, other it doesn't. That's the other thing I want to try. And so that was about this modeling, and these are these correlations. And so my summary points. So OSSL, I'm really proud of it. It's a real community project. People are contributing. I think it's really taking off. The budget is finished for the project, so we do it really now on voluntary basis. The work I do largely on a voluntary basis. But we're very proud that it's really taking off. It's turning into development community. And I think the world desperately needs open source spectral libraries. It needs libraries that people can really understand what is happening. They can reproduce results. They can increase confidence in soil spectroscopy. Anything this black box, and eventually it's difficult to trust. So I think the world needs it. I don't have anything against the companies that commercialize soil spectroscopy. I wish them all the best. I personally, I think it's too risky to do everything really black box. But for them, it's a good business model, and I wish them all the best. But we do want to have also anybody in the world should have access to soil spectroscopy, should be able to use very quickly soil spectroscopy. And as soon as we get a bit more affordable instruments, this infrastructure could be used to really scale that up. If you have GPS coordinates, everybody gets GPS coordinates. If you have GPS coordinates, it's plus minus 20-meter accuracy. We can overlay with the 30-meter resolution data. And if we find correlation, we can do this data fusion. And it seems out that this green band, NDVI, NDCI seem to help with the calibration of soil organic carbon, but we need to do more testing. And that's it from my side. I pass it on to Kostas to talk also about soil spectroscopy data, but focus on Europe.
I think what you have achieved with Jonathan and Jose is very important because you founded this effort in open data and open scripts, and you have created this community around soil spectroscopy. So thank you very much for joining. I decided that this is the appropriate stage to take you a few years back before AI for Soil Health, where we did a campaign and tried to see how we could use field spectroscopy to estimate soil properties. So most of you have probably heard about the story of Pokemon Go, where that this game was not so innocent that asked, it is an assumption that they asked from people to go to remote collection and instead of catching Pokemon to take some georeferenced photos and submit them to Google. And this resulted in creating a very nice data set that trained it augmented reality algorithms, other service about the traffic. And this was one great crowdsourcing experiment. So our question was, could we use this crowdsourcing technique and ask people to go and collect soil spectra for research purposes? So what would we need for this purpose? 3 components. The first component would be a soil spectrometer, essentially a low-cost soil spectrometer like the one that Tom presented before. It's called MEMS. A server that collects all the data and does these machine learning techniques and the machine learning models. So we did a thorough market research, and through the available companies, we selected the one that provided an open SDK because we did not want to build everything in vacuum. We wanted to start an application that was stable and save some time and money. So it's not a publication, advertisement. Here we selected the NeoSpectra sensor from Spectral Engines, which comes in 5 different sensors. To select the appropriate sensor for our experiment, we took a look at spectral data, resampled them in the spectral ranges of each sensor, and tried to develop simple regression models to estimate 5 soil properties like calcium carbonates, clay, nitrogen, organic carbon, and pH. And selected the most appropriate one, the one that had the better accuracy. The sensor that we selected was Spectral Engines NIR1S 2.2, which operates at 17.500 to 21.500 nanometers. And it's fully portable, it's small, waterproof, and it has a Bluetooth connectivity.
How much does it cost?
Around 2,500 euros.
Okay. But you can download the spectra, the raw data you can download.
They go directly to your mobile phone.
Cool.
So, and you do not need any license like NeoSpectra. Also, we selected this spectrometer because there were some shipping restrictions to Greece at this time back in 2019. It was quite hard to make a huge shipment.
The cost is still the same now?
I think probably it has raised a few euros, but no, it's not expensive.
We'll deal with it.
So if we visualize the spectral region that this sensor captures across the full Wageningen spectrum, it covers this range that there is a big absorption depth of water. And according to the bibliography, a paper from our colleague from Aarhus University, Maria Knadel, former colleague, There are absorption bands that are correlated with all the 5 properties. We also developed, we customized the provided SDK and developed an application that each user could use their credentials, and with 2 buttons they could capture the soil spectrum and convert it to reflectance. This application was also in direct communication with a server and automatically transmitted the data captured and converted it to the targeted soil properties. I will not stand in this slide. It is a technology that the database uses. It is a Mongo database and a relational SQL system. And because we intended to use this by non-experts, meaning by people that they participated in a workshop that we trained them, we thought that many errors could be produced and the database could be filled with garbage. So we added a statistical analysis classifier that could identify if the spectral signature capture was not coming from soil. I mean, if someone could measure a different material or the air or improper use. And we trained this dataset with many different objects and many different misusage scenarios. And the classifier had a very nice accuracy. So this is how we try to prevent populating our database with bad quality information. Here how our database management system looks like. Every user takes the spectral signature, and if it is okay, if it is of good quality, it is directly posted. Here you can see the raw spectrum, the white reference, and the conversion to reflectance. And also a machine learning model is calibrated to convert these measurements to soil organic carbon content. And recently we added also the other properties like pH and clay. So where were our pilot sites? We had 3 pilot sites in 2 different countries, 6 in total, 3 in Cyprus and 3 in Lithuania. These pilot sites were indicated by the national paying agents of agriculture payments from each country. And it was the sites that at this period their agents would visit to make field inspections. And we gave them the spectrometers and asked them to collect some physical samples and also spectral signatures of the locations. We didn't select randomly the location. We used the remote sensing data. First, we identified the bare soil through analyzing a time series of Sentinel-2 data about 3 years. And we applied the conditional Latin hypercube algorithm. In order to select representative locations where the field surveyors would visit. Then this dataset was split to 20 to 80 ratio. 20% of them were also physically sampled and sent it back to our laboratory in Greece and analyzed. And all the other locations were just measured for spectral data. Here are some photos from our excursion. And some more about the sampling.
How heavy are these?
It's very small. It's like this.
And what's the weight?
A few grams, less than a kilo. It's pretty small. And here are the results of the database that we built. Here you can see the spectra from the analytical spectrometer. We also have created spectra with the portable spectrometers, of course, and the chemical analysis that we did. It is a pretty much representative dataset, but what was also a limitation that we met. When you are measuring in field, you have to deal with the soil moisture, because as mentioned before, the range of this spectrometer falls directly inside the water absorption band, and this needs to be cleaned. There are many methodologies that you can use for this. One is the EPO algorithm, But what we did, since we had the physical samples measured in the field, we have also asked the surveyors to measure the soil moisture back in them. We also measured them in laboratory conditions, meaning they were dried and sieved. And then we developed a CNN algorithm that maps the spectra collected in the field back in the spectra collected to the laboratory. And this had very nice results because we have also included the information about soil moisture and corrected the spectra with the soil moisture. And this is something that we also intend to do in the AI for Soil Health project. We are currently collecting spectra from different pilots. And this is how we are going to deal with it. And then, since the spectra were mapped back to the laboratory condition, we could also merge with different legacy spectral libraries. We applied also another harmonization technique that I do not want to extend now. It's out of the scope. But this helped us augment our data set and have very nice results in the modeling part. Here you can see the difference before and after applying this machine learning-based correction. And you can see the orange spectrum was the one captured in the field compared to the analytical spectrum captured in the laboratory. And after the correction, you can see that these two lines follow one over the other. And moving on to the modeling part, we got some accuracy compared to the numbers that Tom presented before. For soil organic carbon, it was 0.72, while for clay, 0.77, the pH, 0.76. So to conclude, we suggest that low-cost MEMS sensors are making soil spectroscopy more accessible. And if we combine it with the mobile phones that we all use, this will enable the real-time field-ready data collection. And if it is automated, but for this reason we need open SDKs and not commercial products to support the research, at least. It can be a powerful crowdsourcing tool, and we need more good data for better models. So that's it on my side.
Okay, thank you.
I hope I was also in time.
I love it. So, thank you, Kostas. We still have some time for questions before the time runs out. It's great that this sensor is available. I just want to show just for the end a paper by John and his colleagues how to take. This is MIR based, but you just take a one scan and you estimate all the properties in it. Well, they call it soil health, but it's actually they talk about soil quality. But you could eventually, we could also develop these soil health scores, soil health index, and then we can develop data that you go direct to digital. You just scan it and you say, here's the soil health index. It is possible, but we need to have the training data. You know, we need all this biological data, different lab data. We need a lot of data, and then we can do this. You see, people like Kostas, me, we do this data science, and we can try all the possible models. And if we find a relationship, it's a bingo. So you could directly just scan a soil and say, this is the soil health. The colleagues from Hawaii, they said they got a really good results. R-square 0.91 to estimate the soil health score. So independently scan and soil health core assessment, they get to a high correlation. But it was only in Hawaii, so someone studied it. Yes, that is the soil spectroscopy. But in reality, soil science is also complex. You know, we do want to simplify everything. Everything you can make simple. But some things are complex, and some things you don't correlate, doesn't work in soil spectroscopy. Whoever tries to sell you that, we know you can check our paper, we can show you. We tested all these things. We don't have to sell anything. You know, SSL is open source. We don't sell anything. We don't have to hide the negative results. We show everything, and so some small variables are difficult with source spectroscopy, even with MIR. And also here you see we do these scanners. They do cost few €1,000. Let's say this is still low cost for source spectroscopy, but they don't do miracle. They have a limited accuracy.